Alrighty, having an issue with my chair here, but we're good to go. This lesson is on operations on polynomials, specifically add, subtract, and multiply polynomials. And underneath my face there, it says this is mostly review of stuff that you know. Now, doing it with polynomials is probably going to be new for most of you, but the concepts themselves, like how this works, is all stuff that you've seen before because you've been working in polynomials, because lines are polynomials and quadratics are polynomials. So extending that to bigger polynomials is really an extension of things that you already know, which is good news. All right, so we're going to talk about adding and subtracting first. We're not going to spend too much time on adding because adding is simply combining like terms. And just so we're really clear on what we mean by that, when we say combining, essentially what we mean is add or subtract. Okay, so in this case, it's adding if it's positive. If you see a subtraction sign, you're going to end up subtracting. But that's what we mean by combining. And then like terms mean the same variable part. Okay, so when I say the same variable, I don't mean have an x. I mean that you combine x cubes with other x cubes, x squareds with other x squareds, and x's with other x's, and constants with other constants. So it's not enough that there's just an x there. Okay, you cannot combine a 2x cubed with a negative x squared. Okay, so essentially what we do is we remove the parentheses like so, and you can just do straight removal. I know I've mentioned before that the parentheses are what we call cosmetic. They're separating one polynomial from another, but they're not serving an algebraic purpose. And then you have to go and find the like terms. So I've got 2x to the third plus x to the third. And notice that I am circling the operator there. Okay, that tells me that I'm adding that x to the third. Well, 2x to the third plus x to the third is 3x to the thirds. You are not doing any work like underneath. You're not doing like minus x to the third minus x. You're not doing that because there's no equal sign. Okay. Now in green, now notice again what I did there. I circled the operator in front of it. That lets me know that I am subtracting that. And I scan across to see, do I have any other x squareds? No, I do not. And so it's just minus x squared. Now I have negative 6x plus 4x. Well, negative 6 plus 4 is negative 2. So that'll give me negative 2x. And then last but not least, I have 1 minus 3. Well, 1 minus 3 is negative 2. And so that's what you're doing. If you want to pause here, most Algebra 2 students are pretty good with the idea of combining like terms, but I do have students every year that are not actually very comfortable with this. And so it might benefit you to just stop and look at the colors, like how I color coded that. And if you caught all the like terms, everything should be circled. If you get to the end of the problem and something's not circled, you want to double check and make sure that you did get that one. Okay, so with subtracting, you distribute the subtraction and then you combine like terms. So they're really very much like the adding, except for this step here that like kind of front loads it. And this comes from the idea that subtraction means adding the opposite. And so when you have the adding the opposite, that's like your keep, change, I guess is what it was. And so you change the subtracting to adding, and you take the opposite. So you flip the sign. That's essentially what you're doing there. So you've got a positive 6x squared. That's going to become negative 6x squared. When you distribute that negative, your negative 2x is going to become a positive 2x. So you're distributing that subtraction so that you're subtracting everything. Other than that, it is the same as your adding. So your first set of parentheses can just be removed. And then what you're doing is this. You're subtracting the 6x squared, you're subtracting the negative 2x, and you're subtracting the 3. So that subtraction is going all the way through to everything. this right here, we normally would not write. So I would not normally write minus the negative 2x, because to subtract a negative does mean to add. And so typically right in there, we would just say plus 2x. Okay, we wouldn't do the minus negative, but I want everyone to know where the plus comes from. Okay, we don't want like random plus signs popping up. And then we do the same thing. So we just combine like terms. So I have 4x squared minus 6x squared. That gives me negative 2x squared. We'll do this one in green. Negative 3x plus 2x. Negative 3x plus 2x will give me negative 1x, or you could just write negative x. And then my last one here is 4. I was going to change the color up and I clicked on, there we go. 4 minus 3, and 4 minus 3 is 1. And of course you don't have to write the 1 out in front. That could just be minus x. Okay. Either one of those is equally correct. Now with subtraction, I am going to take you through a, like how you can do this with algebra tiles. And for some of you, this is unnecessary. So if what I just did was good, you're like, I got that, I'm ready to do it, distribute the subtraction, combine like terms. Then the next part, I don't want to say you can fast forward through it, because I think all students benefit from seeing it, but you're just going to watch it with an eye towards, okay, I'm just going to see how the model works. All right. So algebra tiles can help some students visualize the subtraction. And the one we're going to do here is 2x squared plus 4x minus 3 minus 4x squared minus 2x plus 2. With the tiles only go up to x squareds. So this only works for up to quadratics, but it might be beneficial. So the first thing you would do is just model what that is. If you take a look at what we got there, so here we have 2x squared plus the 4x minus 3. So I took that quadratic and modeled it. And then I'm going to subtract from that the second quadratic, which is 4x squared minus 2x plus 2. Okay, so that's what we're going to be subtracting. So the first thing I did was I just took each of the polynomials, modeled them, and we put a subtraction sign in the middle. Now, that was eloquent. The distribution of the subtraction is modeled by flipping all the tiles over. So that step where you're taking the opposite of everything, you're going to take the 4x squared and flip all the tiles over. You're going to take the negative 2x and flip the tiles over, and the 2 and flip the tiles over. That's how the subtraction is modeled. So that ends up looking like this. So I had those blue tiles, they are now flipped over. I had red ones here, flipped over and flipped over. So instead I have negative 4x plus 2x minus 2. If you take a look at what that would be algebraically, you'd be subtracting the 4x squared. Subtracting a negative means like you're flipping them over. So the negative 2x's became a positive 2x. And subtracting the 2 means that you have the negative 2 out here. And that means now you're just going to combine them, meaning you're adding them. So that adding them. So what we're doing now is combining like terms. So I really like that little bit of nuance. And even if this is not something that you need to do, it's not a bad thing to look at. It's really not a bad thing for you to look at, where you've got the flipping of the tiles. Now you combine the like terms by finding the zero pairs. So you're going to look at all like the big squares and see, like, do I have a positive and negative that cancel each other out? Look at the rectangles, see if they cancel out, and the units. This one actually turned out to be kind of boring. So I grouped them all together. So it turns out we've got some zero pairs with the big rectangle or big squares. And then these all just pulled together, like nothing was canceling out. And then my answer is whatever's left over. And so this chunk right here would be the answer. So remember, that's the problem that we're doing. And this is my answer. And so that is this. It's negative 2x squared plus 6x minus 5. So there you go. So I think that is a neat thing to walk through. Now, do I recommend the tiles? Not always, but if you meet one of these criteria, I think it's worth checking out, especially for things that just have quadratics. So if you tend to struggle to visualize like terms, the different shapes can help. If you find that you will sometimes take an x squared and combine it with an x, well, you can't do that if the x squareds are like big squares and the x's are rectangles. Like you're not going to make the mistake. If you tend to just forget to distribute the negative, the act of flipping can help. Okay, so you're probably not going to forget if you're flipping all of them over. Or if you tend to make sign errors, the act of finding the zero pairs can help. So that idea of I've got some are positive and some are negative, combining them and looking for the zero pairs to see what's left over. And then all students benefit from having a model. So even if you don't use the tiles, if you envision in your head, this is the step where I would flip them. Now I'm looking for zero pairs, like what would those zero pairs be? Can help you picture the combining of the like terms and so forth. So all students benefit from that, which is why I wanted to include it in the lesson. Even if you don't need the model, having the model is always pretty good. Now for multiplying, we're going to camp out with like multiplying for the rest of the lesson here. I'm going to tell you straight up, use the area model to structure it. So this is kind of a brutal problem. This is a 4-term multiplication, like polynomial times a 3-term one. This is about as ugly as it can get. And so if you can hang with me through this, it'll be okay. So I'm going to do a big area, okay? And I'm going to do the 2x cubed minus 4x squared plus x minus 1 across the top. And I need a column for each of those. And then I'll do the x squared minus 4x plus 3 going down the side. And you could, of course, do it either way. Because it doesn't matter what order you multiply in. So you could have like your rectangle looks like this, or your rectangle looks like this. Like it's the same rectangle with the same area. And now you've got all of these multiplications to do. So there's actually 12 different multiplications that you need to do, one for each of the boxes. But you've got it structured well. Okay, so this is pretty good. It's not fun, but yeah. So 2x to the third times x squared. Okay, so if you're wondering, like, what is that? I'm going to do a little bit of scratch work off to the side here. Okay, you do not have to do this, but I've got 2x to the third. Remember, x to the third is x times x times x times x squared. And if you look at that, it's going to be 2, and then notice that we have 5 x's there. So we haven't really done the laws of exponents yet, but essentially you're going to end up adding the exponents. If you have x squared times negative 4x squared, okay, that would give you this. It'd be like x squared times the negative 4 times 2 more x's, and you can tell, oh, I've got 4 x's there. So that would be negative 4x to the fourth. Now I won't do any more of them out. If you want to pause the video right here and just look at that scratch work, so you can follow along for future problems, go ahead and do that. All right, and you can of course rewind the video. I cannot rewind a time, but you can rewind a video. All right, so the next one is x squared times x. That would give me x to the third, and x squared times negative 1 is negative x squared. Now that was like kind of the roughest line. The rest of them, well, they are what they are. So 2x to the third times negative 4x. 2 times negative 4 is negative 8, and then I'll have a total of 4 x's. Negative 4 times negative 4 on the next one is 16, and then I have 3 x's, so I have the x and the x squared. Negative 4x times x is negative 4x squared, and negative 4x times negative 1 is positive 4x. And then the last line, finally, it's a constant. So 3 times 2x to the third, 3 times 2 is 6, so that's 6x to the third. 3 times negative 4 is negative 12, so that'll be negative 12x squared. 3 times x is just x, and 3 times negative 1 is negative 3. So not fun, but there's a couple things that are really, really nice about this that I want you to notice. Notice that my highest exponent is up here in the upper left. That's going to become very, very important when we do division, okay? And then notice this. My x to the fourths, the ones that I need to combine, they're right here on the diagonal, okay? So you don't have to like hunt all over the place. Your x to the fourths are all right there. Your x to the thirds are all right here on that diagonal. Your x squareds are right there on that diagonal. Your x's are there on that diagonal. And then down here, you have your constant down in that corner. And that is a really, really helpful and useful pattern. So this guy will always be solo, and this one is always solo, unless, I guess, I want to say always. This is going to be really rare that they're not solo. So you can start with the 2x to the fifth. All right, that's going to be the first term. And then if you're not sure, grab your calculator and you can just do -4 plus -8. Okay, -4 plus -8. That's going to give you -12. And so the next term is -12x to the fourth. And again, grab your calculator if you need to. 6 plus 16 plus 1, okay, is going to give me 23, but you can grab a calculator. So 23x to the third. Right here, -12 plus -4 plus -1, okay, or -1, that'll be -17. So -17x squared. And then, of course, I run out of space over there and inadvertently change colors. So go me. And then we get to the normal ones. 3x plus 4x is just 7x. And then the -3 is solo. So notice that. Now, I did say at the beginning of that problem, that's about as ugly a multiplication problem as you could ever hope to ever not want to do. So chances of you seeing something that awful on a like a test, very minimal because it is a very long problem. But what I want you to see is how the area model does structure that, and particularly this feature where all the same variable parts land right on those diagonals. Really, really nice. So you're thinking, man, Miss Taylor, I don't like the area model. I told you I didn't like the area model. I want another way to do it. Well, here is your alternative. Okay. Now, if you go and look at this line, okay, remember this had like 12 things in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the same 12 things that were in the area model, and they were gotten the same way, sort of. Basically, you would have to distribute and then distribute again, okay, and then distribute again, and then distribute one last time. All right, so you would have this string of this distributions, and it would land you with this string of things, which is the exact same thing that is in the area model. And then you would combine all the like terms and you would land at that same answer. But notice how long the problem stretches horizontally. Okay, I type wrote this because I didn't think there was probably any chance that if I were handwriting it on the screen that I would be able to fit it like going across the screen. It's really, really long if you opt to do it that way. And your like terms are not near each other. So as with the area model, you got the 2x to the fifth that's going solo and the -3 down at the other end. These would have been in the opposite corners, but everything else is like a jumbled mess. So if you're looking for, say, your x to the thirds, there's one of them right here. Then you have to jump over one. Then you have to jump over another one. Okay, and you got to collect them, but they're not next to each other. Your x to the fourths, your x squareds, nothing is next to each other. All of it is like split up with other stuff in between them. So this makes the structure much, much, much more error prone than organizing it on that area model. If you want to do it this way, you do you. All right, you do you. I'm just cautioning you, it's really easy to miss one of the distributions. So you've got to like line your track your eye over, and you have to do it over and over and over again. And it's so easy to miss one of them. You just miss one. Okay, your eyes miss and your eyes can miss it here. When you organize it on the rectangle, every one of those 12 multiplications has its own box. You're not going to forget one. Okay, you're not going to forget one because there'll be an empty box on your model. This one, if you forgot, say, the x cubed, nothing would tip you off that you missed it, aside from the fact that there should be 12 of them. Okay, which you get from saying I multiplied something with 4 by something with 3. And you can count. And then like if you realize, oh, I'm missing one, you don't even know which one you missed. Like you have to go back through the whole thing. So not gonna endorse this, but yeah, just much better to structure it on the area. Now with the area model, like terms are often on the diagonals, but not always. So I really wanted to point that out to you, that you had like your x cubes and everything like all like arranged on the diagonal, but I want it to be clear that it's not always like that. Will it often be like that? Yeah. So here's an example of one where they don't end up on the diagonals. Okay, so we've got x cubed plus 2x squared, or minus 2x squared plus 4, and then we have the x minus 3. So x times x to the third would give me 4 x's there, so x times x, 4 of them. Negative 2x to the third and 4x. And then in my second line, negative 3 times x to the third is negative 3x to the third. Negative 3 times negative 2x squared is positive 6x squared. And negative 3 times 4 is negative 12. And you still have some of the diagonal stuff going on. So you got the x to the fourth and the x to the thirds are on the diagonal. But on this diagonal here, you've got an x squared and you have an x. Okay, so you just want to be alert to that. And then the negative 12 is hanging out where we expected it to. So when you go to write the answer, it's x to the fourth. And you can even put like a little x through that. Here's my like term. So negative 3 plus negative 2 is negative 5. And then right here, these guys are riding solo. Okay, they're on a diagonal together, but they are not like terms. So they would just go in there, and then you have the minus 12. Now, when does that not happen? Like you end up with them not on the diagonal. Here's the thing that tips you off that they're not on the diagonal. If you look at this polynomial, okay, where my cursor is circling there, we've got x to the third minus x squared. Notice that the x is missing. It goes from x squared all the way down to the constant, and you're actually missing the x term. And because it's missing the x term, it translates into this little hiccup in the rectangle. If we had had the other term, we would have had like another column out, and we would have had x squareds and then x's and then the constant. But it shortchanges us a column or a row, depending on which way. So you're missing one of the columns, and when you're missing one of the columns, it ends up kind of collapsing it. Okay, so not like a huge deal, but just like a little bit of a caution. Yeah, a little bit of a caution. So that's it for the lesson. So here's the practice set. So the directions for numbers 1 through 7. Perform the indicated operation on each set of polynomials. So make sure you notice like if it's plus, minus, times. Okay. So I think I gave you 2 or 3 of each. With 7, it must be 2 or 3. And they range from like fairly simple to messier. Okay. Question 8 is a question about how the models work. Now for numbers 9 and 10, we're going to go back to our AI. All right. For numbers 9 and 10, identify the error. You may identify it and explain it yourself. Okay. That is entirely okay for you to do. So you look at number 9, look at the problem, look at the answer, and you explain what is going on. Okay. Don't just tell me the answer is wrong. I know the answer is wrong. There's an error in it. Okay. So don't say, well, the answer, it's wrong because it's wrong. It's, yeah. Or what do I get sometimes? The mistake is that you did it wrong. Thank you. Like, mistake is that I did it wrong. That's not helpful. Or if you want to use AI, what you would do is take like a screenshot. So you guys know at this point how to use the snipping tool. Go and snip it and then put it into Copilot or ChatGPT. Okay, if you're doing this from home, and say, what is the error in this? And then ask for clarifying, for it to clarify. So don't just like copy down whatever it says first. If you don't understand what it tells you the error is, ask for clarification, and then you're going to share with me what Copilot did. Tell me on your homework whether or not you use Copilot. Okay. And the skill that I want you guys to develop here is the skill of using AI not to do the work for you, but to help you assess work that's been done, to see like how you could get explanations. So the idea, like long run, is that you would put your own work, like take a photograph of your work that you're doing, and asking AI to basically tutor you in it. Like, can you grade this and give me feedback? Like, what did I do wrong? What do I need to fix? So the long range goal there is for you to like empower you to use the AI. But for this, like, you can do it yourself or use Copilot, and just let me know. Okay. As always, you guys know where to find me, and let me know if you have questions.